Elasticity. A substance is elastic if it returns to its original size and shape after the deforming force on it has been removed. Elastic substances obey Hooke's law of elasticity. Hooke's law of elasticity states that provided the elastic limit of a substance is not exceeded, the extension produced is directly proportional to the applied force. Force is directly proportional to the extension. F here represents the force directly proportional to E, which is the extension. Force is equal to constant K times extension. This is our equation 1, where K is called the force constant of the elastic substance. Force constant is the force that produces a unit extension in a substance. The unit is Newton per meter. From the equation 1 above, we can also get that the force F1 on elastic material which produces extension E1 is also equal to the force F2 that will produce extension E2, following this equation, which we call equation 2. Force constant K of an elastic substance can also be determined from a force extension graph. The graph is shown here. The slope of this graph is the change in the applied force dF divided by the change in the extension dE. Force constant K is equal to the slope of the force extension graph. Work done in an elastic substance is equal to the elastic potential energy stored. Work done is equal to elastic potential energy, and that is equal to the average force times the extension. Work done is equal to half Fe, or half Ke squared. K is the force constant of the elastic material. Tensile stress is the ratio of the applied force to the cross-sectional area of the elastic substance. Tensile stress is equal to the applied force divided by the cross-sectional area. Tensile stress is equal to F over A, F divided by the area. The unit is Newton per meter square. Tensile strain is the extension produced per unit length of the elastic substance. Tensile strain is equal to extension divided by the original length of the elastic material. Tensile strain has no unit. Young modulus, represented by letter E. This is the ratio of the tensile stress to the tensile strain. Young modulus is equal to tensile stress divided by tensile strain. Young modulus is equal to F divided by A, that's the tensile stress, divided by extension divided by the original length. By the time we combine the two together, we have young modulus E equal to the product of FL, that's the force times the length, divided by the product of the cross-sectional area and the extension. The unit of Young modulus E is Newton per meter square. Young modulus is equal to force divided by the extension times the length divided by the cross-sectional area. That's my equation 3. From equation 3 above, we now get another important relationship. For Young modulus is equal to the force constant times the ratio of the length to the cross-sectional area. K is the force constant. Example 1. A force of 15 Newton stretches a spring to a total length of 30 cm. An additional force of 10 Newton stretches the spring 15 centimeters further. Find the natural length of the spring. The options are A, 25.0 centimeters, B, 22.5 centimeters, C, 20.0 centimeters, and D, 15.0 centimeters. The solution to the problem is as follows. Solution. Assuming the spring obeys Hooke's law of elasticity, F, the applied force is equal to the force constant times the extension. That means the ratio of the applied force to the extension is always constant. That equation can be written as F1 over E1 is equal to F2 over E2. This we take as our equation 1. Let's look at the question so we can get the information from there. The applied force F1 is 15 Newton. Then we are told that upon application of this force, the new length of the spring, which is the sum of the original length and the extension produced, is 30 cm. So new length is 30, will give us the initial length plus extension 1. From here we get extension 1 is 30 minus the original length of the spring. Also, we are told that an additional force of 10 Newton created a new extension. So the force F2 will give us the initial force plus the additional force of 10 Newton, that is 25 Newton force. The new length after the application of this force is the natural length plus the new extension E2. And that new length is 30 plus 5 because we are told that it stretches it 5 cm further. This one is 30 plus 5 will give us the natural length plus extension E2. 35 is natural length plus extension E2. Extension E2 will give us 35 minus the natural length. Substituting data into equation 1 above, we have F1 15 divided by extension E1 30 minus L should give us F2 25 divided by extension 35 minus L. Cross multiplying, we have 5 into 35 minus L should be equal to 25 into 30 minus L. This will give us 525 minus 15L should be equal to 750 minus 25L. When I collect like terms together, we have 25L minus 15L will give us 750 minus 525. 10L is equal to 225. L, the natural length of the spring, is 225 divided by 10 centimeters, which is 22.5 centimeters. By this working, option B is the correct answer. Example 2. We have a graph here. Graph of force against extension X, with the values used in plotting the graph stated. The diagram above represents the graph of the force applied in stretching a spiral spring against the corresponding extension. The force constant of the spring is dash. Option A, 40 Newton per meter. B, 30 Newton per meter. C, 20 Newton per meter. D, 10 Newton per meter. The solution is as follows. Solution. The force constant represented by K is the slope of the force extension graph. Therefore, the force constant is equal to change in the force divided by change in the extension produced. So K will give us 120 minus 80, that's the change in force, divided by 6 minus 4, that's the change in extension. That will give us 40 divided by 2, and that is 20 Newton per meter. Therefore, option C is the correct answer. Option C is correct. Example 3. A load of 20 Newton on a wire of cross-sectional area 8 times 10 raised to power minus 7 meters square produces an extension of 10 raised to power minus 4 meters. Calculate the Young modulus of the material of the wire if its length is 3 meters. Option A, 7.0 times 10 raised to power 11 Newton per meter square. B, 7.5 times 10 raised to power 11 Newton per meter square. C, 8.5 times 10 raised to power 11 Newton per meter square. And option D, 9.0 times 10 raised to power 11 Newton per meter square. The solution to this problem is as follows. Solution. First, let's consider the data as the information we can get from the question. The load is the force applied. Force F is 20 Newton. Then the cross-sectional area is 8 times 10 raised to power minus 7 meters squared. The extension produced, represented by small letter E, is 10 raised to power minus 4 meters. Of course, the original length of the wire is 3 meters. From this information, we can get the tensile stress and the tensile strain. Tensile stress is the force acting on the wire per unit area. So this will give us 20 divided by 8 times 10 raised to power minus 7. So the tensile stress is 2.5 times 10 raised to power 7 Newton per meter square. Next is tensile strain. Tensile strain is the extension divided by the original length. This will give us 10 raised to power minus 4 divided by 3. The answer is 3.33 times 10 raised to power minus 5. With these informations, we can get Young modulus. Young modulus E is tensile stress divided by tensile strain. And this will give us 2.5 times 10 raised to power minus 7 divided by 3.33 times 10 raised to power minus 5. Young modulus E is equal to 7.5 times 10 raised to power 11 Newton per meter square. By this solution, option B is the correct answer. Option B is correct. Example 4. In an experiment to demonstrate Young modulus for a wire, several loads are attached to the wire and the corresponding extensions measured. The tensile stress in each case depends on the A, load and the extension, B, load and the radius of the wire, C, radius of the wire and the extension, D, extension and the original length of the wire. To determine the tensile stress of a wire, the informations needed are that of the load or the applied force and the cross-sectional area. So before we take a decision on the right option, we have to recall that tensile stress is equal to the force or the load divided by the cross-sectional area. Cross-sectional area. To determine the cross-sectional area, the radius of the wire is needed. This is obtained by using the micrometer screw gauge to measure the diameter. Thus, the information that will give us the tensile stress of the wire are the load and the radius of the wire, which is used to determine the cross-sectional area. The load and the radius of the wire is required to determine the tensile stress of the wire. Note, the area A is a function of the radius, is pi r squared. That's where we apply the radius, then the load. Those two informations will be used to determine the tensile stress of the wire. Therefore, option B is correct. Option B is correct.